Chapter 4 is about dimension reduction. Dimension reduction refers to the process of reducing the number of predictor variables, number of x variables. So if you have too many x variables, that will lead to certain problems in the analysis. So it is a good idea to try to reduce the number of variables, and what are the different ways in which we can achieve that, and that's the topic of this chapter. So dimensionality here means what? The number of variables, x variables or predictor variables. Okay, so it is the number of variables in the data set, the predictor variables. Now it can grow due to derived variables, even if we start with just like say 20 variables. If you have categorical variables in them, then each categorical variable, okay, will have to be converted into dummy variables. So if a categorical variable has 10 unique values, okay, for example, college major, that column has 10 different possible values. Then you have to define 9 dummy variables, m minus 1. So one variable is now going to be replaced by 9 variables. So if you have several categorical variables, even if you start with just a handful of variables in the beginning, you can very soon end up with a really large number of variables. So it is a problem that we have to deal with. What happens when you have too many variables in the data set? So too many variables often leads to overfitting. Overfitting here is something that was covered in the previous chapter. That is when you try to fit too close to the training data that is available to us, which means that you are actually fitting the random variation and not the underlying model itself, underlying relationship. So if you have too many variables, you end up modeling the random variations rather than the underlying relationship between the variable and the target. So you have that's reason to avoid overfitting. And of course, when you do overfitting, you end up with problems of accuracy and reliability. Because overfitting, you will get a false sense of confidence that your model is doing very well, because of the training, it fits perfectly. But then when you apply the model for score data, and you end up with a lot of error, and so reliability will suffer. And if you have lots of variables, that will lead to multicollinearity. Multicollinearity here refers to correlation between pairs of variables, pairs of predictor variables, or a group of variables. So when you have correlations among the predictor variables, if you want predictor variables to be uncorrelated with each other, if they are correlated with each other, then they are competing with each other for the prediction, in the model, a place in the model to predict the target. So when you're competing with each other, you may end up with unreliable coefficients, unreliable predictions. And if you have too many variables, of course, you'll have computational problems, because the matrix becomes really large, and it leads to inefficiencies. And if you have lots of variables, of course, there is a problem of collecting. When you deploy the model in production, you have to have values for all those variables in the score data. And that can be expensive, time consuming, and may also lead to more variables, more data, more possibility for error. So cursive dimensionality described here. So if you have one dimension, there is only one variable, and all the values fall along that one variable line. So the variance is quite small. Okay, if you add another dimension, then it gets spread out a little bit. So the space between values increases. In a 3D model, and the values are even farther apart. So in 100-dimensional space, they would be like distant galaxies. So which means it's harder to find relationship among those variables, among those points. Now, how do you mitigate cursive dimensionality? Okay. consult with domain expert, meaning that you have a list of 100 variables. You sit down with the domain expert and see which variables can be thrown out, which variable are not completely extraneous and need not consider, throw them out. Yeah. Which variables are important, which variables are useless, and then you can do exploration with the data, then see which variables have too many missing values, which variables have too many errors in them, and which variables cannot be measured in the future. Okay. And those kinds of variables can be thrown out. So which variable can be measured before the outcome? Okay, this is a key point. So if a variable can be measured only after the outcome being the target, then you cannot have that ahead of time to predict the target. For example, house price. You're trying to predict house price in the Boston housing example. Now, tax is one of the variables in the data set. But tax comes after you determine the housing price. So the house price is determined, and then you multiply by the percentage of tax. So the tax is measured after the outcome. So this variable can be measured. It cannot be measured before the outcome, the tax on the house. So tax is not a variable that we can use in the analysis, and it should be thrown out.